Hello students, welcome to this section. Now in this section we'll continue in discussing the armature winding terminologies we have started to discuss in the previous video. Now let us continue. And as you remember, in our last time videos we have discussed some terminologies like turn, coil, winding, pole pitch, coil span. We define them, and I have tried to just show you what they are physically. Now we'll continue. The other important term in this armature winding is back pitch. This back pitch means it is a distance measured in terms of armature conductor between two sides of the coil at the back of the armature. At the back of the armature, this important term. Example, see this. This is one coil, and this is another second coil. So the distance from the first coil side to the second coil side, this YB, this distance we call it is back pitch. This is the back side of the coil. The back side, it is called back pitch. And the distance from the second coil first side to the first coil second side, we call it is a front pitch. This is a front pitch. And the difference of the two we call resultant pitch. Difference of the two. Just to support it with an example, if a coil is formed by connecting conductor 1 to conductor 12, these two conductors, if they were connected together at the back of the armature, then the back pitch is going to be the difference of the two. It is going to be 12 minus 1, 11 conductors. That is a back pitch conductor. And for example, if the coils are formed by connecting coil side 12 and coil side 3, if coil side 12 and coil side 3 are connecting together on the same commutator segment, if these two are connected on the same commutator segment, then the front pitch is going to be the difference of the two, 12 minus 30, 9 conductors. See this. This coil side is connected at 1, coil side 1, and it was connected with 13. See, and the back pitch, it's going to be the difference of the two. This is the second coil side is at 8 and the first coil side is at 1, so the back pitch is going to be the difference of the two, 8 minus 1, 7. And in this case also you can see it is at 1 and it is at 8, so the difference of the two, it is going to be 7, which is the back pitch. When you come to the front pitch, and this coil side, this is wave type. This is a wave type of winding normally. So if the first coil is at 1 and this coil side will be at 8, and second coil is at coil 30. So the front pitch is the difference of these two, 30 minus 8, and in this case also it is 8 minus 3. So this is how we can know the back pitch and the front pitch. These two terms are very important when we design and try to put or determine the coil placement inside the slots, inside the slot. And the other important point is commutator pitch. It is the distance between segments to which the two ends of the coil are connected. Two ends of the coil. This is the starting of this coil, then it gets end up at this commutator. So the distance between these two is coil end, it is called commutator pitch. This is a lap winding. When you come to the wave winding, this is the first winding, the first starting of the segment, I mean the end for the commutator coil end. It starts here and it ends here. So the distance between this and this we call it is a commutator pitch. Commutator pitch. In a lap winding, the commutator pitch is a difference of back pitch and front pitch. It is a difference of back pitch and front pitch, whereas it is the sum of back pitch and the front pitch in wave winding. In a wave winding. So if that is the case, since in a lap winding the coil ends are connected to consecutively to the next commutator segment, so the commutator pitch in lap winding is going to be 1, and for that of simplex wave winding it is going to be 2 pole pitch or segment. 2 pole pitch or segment. Another important term is progressive winding and retroprogressive winding. The progressive winding is one in which the connection to the commutator will progress around the machine in the same direction as being traced along the path of each individual coil. See this, for example. When you see the first coil, it was started at this segment and ends to the next segment, and again the second coil is connected to this point, again it go forward to the right side for myself, right? Forward, again it keep on continuing like this. So the number of the first coil side of the coils are going to be progressed in front or to the right side, and the commutator are increasing to the right side. They are increasing this side. I think better term if I have okay, it's not there, maybe. Okay, I'll come to it later on. Anyhow, so if the windings are progressing from the first commutator to the next to the third to the fourth, like this, to front side, we call it is a progressive type of winding. In this type of winding, back pitch is greater than front pitch, and the commutator pitch is going to be +1. But when you come to the retroprogressive winding, when you come to that, if you see this, this winding, for example, it starts from this commutator segment and ends to back commutators. It was starting here, but it ends here. In a case of the progressive, it starts here, ends here, just going forward. But this one is going backward. And this coil, it starts here, and if you trace it back, it ends here. So it is going back side to the left side. It is going this side. That is, we call it retroprogressive winding. Retroprogressive winding. So in a retroprogressive winding, the front pitch is greater than back pitch, and the commutator pitch is equivalent to -1. A retroprogressive winding is seldom used because it requires more copper. It consumes more copper, so it's not advisable. Rarely we use it. These are the general rule for DC armature winding. We have to have these rules also in our mind. So in a design of DC armature winding, whether it is lap or wave winding, the following rules may be followed. 1. Back pitch and front pitch should be nearly equal to pole pitch. Nearly equal to pole pitch. In case of the fractional pitch, it is not going to be equal, but if it is a full pitch, it's going to be equal. But now in this case, in any of these armature winding, the pole pitch and the front pitch should be nearly equal to the pole pitch. This will result in increasing EMF in the coil. That is the first important point. Second, both pitch, back and front, it means, should be odd. They should be odd number, so that every coils will get connected to the segment, and we have to make sure that none of the coil side or coil in will left outside. So this will permit all end connections between the conductor at the top of the slot and one at the bottom of the slot. And the third point, the number of commutator segment is equal to number of slot or coil. That is, number of commutator segment should equal to number of slot. That should also equal to number of coil. This is because each coil has two ends and two coil connections are joined at each commutator segment. There has to be equality, means they have to be equal to be connected to each other. And the other point, the fourth point, is the winding must close upon itself. It should be closed circuit winding, so that the continuity of the current flow have to be ensured in the machine. That is very important point. And you have to go through this relation between pitch for simple lap winding. They are almost summary of the point is what I have said before. The back and the front pitch are odd and are of opposite sign. They could not be equal. They differ numerically by 2. And both back pitch and front pitch should be nearly equal to pole pitch. Average pitch is also there, which is the sum of the two divided the sum of back and the front divided by 2. It equals pole pitch, which is Z by P. And the commutator pitch can be +1 for progressive, -1 for retrogressive. And you have to just go through these points and extra points normally, which is not there in the curriculum, but it's very important. Better you go through it. And our next point is an example. Draw or develop a diagram of a simple 2-layer lap winding for a pole generator with 16 coils. Now this generator has got 4 pole with a 16 coil. So the number of commutator segment is how much? It's 60, because it's equal to number of coils, we say. And the number of commutator conductors or coil side is going to be twice of the slot. That's obviously 32. 60 by 2. And what is the pole pitch? Pole pitch can be number of slot divided by pole, and or it can be number of coils divided by pole. So now in this case, in order to draw this design this winding, we have to remember these formulas: front pitch formula and back pitch formula. Now, according to this, our front pitch is 7, our back pitch is 9. Now we have to plug everything, it's already there. So number of conductor is 32, and number of pole is 4 minus 1, it gives you 7 and 9. So in a simple lap winding, the winding is 2-layer and lap winding type. So let us see where the coil sides are going to be placed. For example, if we start with coil side 1 at the back, coil side 1, or we can start from the front also, doesn't matter. So the next back is going to be connected to 1 plus the back pitch, which is 9. So 1 plus 9 is going to be 10. So this one segment is going to be connected to 10 line segment, 10 coil side, the coil side, and the front one should be 10. If we want to use this front one, it was 10, the front one, so we have to subtract the front pitch. So it was 10 and the front pitch was 7, so it is going to be 3. So if you see the windings, see this is the overall winding. I was using first coil side 1, and since it is a front, it's the front side, it's the back side, so 1 plus 9, 10. The next coil side where it is going to be connected, 2 coil side 10, this one, this 10, see, it's 10. And if you want to use the front type, 10 minus 3, what we said here, it was 10 minus 7 is going to be 3, right? So if you use it, the front pitch 10, okay, sorry, let me come back, not to confuse you. And similarly, if I start with 3, I will end up with 12. See, if you start with coil 3 plus 9, it is going to be 12. This is 12. And if you start with 4, for example, the down one, 4 plus 9, it's going to be 13. See, 4, this is a 4, right? This is a 4. No. The next winding is simplex wave winding. Under this, the series or the wave winding is an alternative way to connect the rotor coil to the commutator segment. It's an alternative way. And in this winding, we connect end of one coil to the starting of another coil of the same polarity as that of the first coil. So if you see this AB, it is connected with this commutator segment and end here, and the other coil will continue in the same fashion, and the starting of this and this are under the same pole, it says. In this type of winding, the coil side AB progresses forward around the armature of another coil side and goes on successively passing through N and north and the south, successively passing through it pole until it returns to a conductor A1 B1 laying under this starting pole. It will successively continue until it returns back to this under the same pole. Because the winding progress in one direction round the armature in series of the wave, it is known as wave winding. Since we connect the coil in series, here we call it is a series winding also. Windings are connected in series. It's also called a series winding. Wave also classified into progressive and retroprogressive. If after one round of armature the coil fall in a slot right to, it is a straight slot, the winding is called progressive. This is a progressive type. Right? It's progressing ahead, just it's moving this side. It's moving this side. And in case of retroprogressive, it is moving back side to the left side. In my case, to the left side, it is moving back. See, it is moving back, and this is going forward. That is a retroprogressive and a progressive. Here in the picture we have since the second round, we'll come to it later on, this one, and these are pointers which we have to understand in a simplex wave winding. The following point regarding simplex wave winding should be carefully noted. One, average pitch is going to be YB plus YF by 2, back pitch plus front pitch by 2, and both pitch YB and YF are odd and the same side, they are opposite in a lap, and resultant pitch is going to be the sum of the two, and the other terms you have to understand them and go through them normal. This is an assignment which you are supposed to work and submit after we did all the examples. Let us see the use of lap and wave winding. The advantage of the wave winding is that for a given number of poles, the armature conductors, it gives more EMF than lap winding. So, which produces more EMF? Wave winding. Conversely, for the same EMF, lap winding would require large number of conductors, which will result in higher winding costs and less efficient utilization of space in the slot. Hence, wave winding is suitable for smaller generators, especially those having 5 to 600 volt DC. It is advisable to use this. Another advantage in a wave winding is that equalizing connections are not necessary, where in the lap winding they are definitely important. That's another important point of the wave. And the lap winding armature, in the lap winding armatures, unequal voltage are produced, which set up a circulating current that produces sparking at the brush. However, when large currents are required, it is necessary to use lap winding because it gives more parallel passes. If there are more parallel passes, our current will increase. If current increase, our EMF will be very high. Hence, lap winding is suitable for comparatively low voltage but high current generator, where wave winding is suitable for high voltage and low current machines. To summarize points what I said, see, lap winding and wave winding comparison. Number of parallel paths in a lap winding is equal to number of poles. We said this before. But in a wave winding, number of parallel paths is always 2. It's always 2. Second, the number of carbon brush in lap winding is equal to number of poles. But in a case of wave winding, number of brushes always 2, because number of brushes is equivalent to number of current paths. It should be equal. That's always 2. Third, lap winding are used for low voltage and high current, and whereas the wave winding is opposite of this: high voltage, low current. See, high voltage and low current. And the fourth one, EMF generated in lap winding is independent of the number of poles. Is independent of the number of poles, but EMF generated depends on the number of poles in the lap winding. Lastly, lap winding is more costly than a wave winding because it requires additional equipment like equalizer rings, and more carbons are required because it depends on the number of passes. But in this case, it is comparatively cheap because it uses only 2 brushes. So comparatively, this is cheaper, we can say. That is a comparison. Next, we'll discuss about the motors, or DC motor. This is what I have. So the next section we're going to attempt the 2 examples, one for a lap winding and the other for a wave winding. So you try at your home, and we'll try to attempt it in the class with together. Just try to understand this as much as possible. That is what I have for today. We'll continue next. Thank you very much for listening.